Welcome back to another episode of Data Insights, where we explore the fascinating world of data systems and their evolution. Today, we're diving into some intriguing concepts like the ability to replay historical events, the importance of exactly once semantics, and the ongoing conversation about traditional databases versus Unix-like systems. So, grab your headphones and settle in for a thought-provoking discussion about the future of data systems. Let's start by talking about the ability to replay historical events using modern processing engines. Imagine if you could revisit past data streams as easily as scrolling through your social media feed. Thanks to log-based message brokers, this is becoming a reality. These systems allow us to replay messages and even read inputs from distributed file systems like HDFS. This capability not only enhances our understanding of past data, but also provides a solid framework for analyzing trends and making informed decisions based on that historical context. Now let's shift our focus to exactly once semantics in stream processors. This concept is crucial because it ensures that the output remains consistent even when faults occur. Think of it as a safety net for data processing. If something goes wrong, the system can discard any partial outputs from failed tasks, ensuring that the final result reflects a scenario where no faults happened at all. This level of fault tolerance is similar to what we see in batch processing, where reliability is key. Maintaining data integrity through exactly once semantics is a game changer for businesses that depend on accurate data for their operations. Next, we need to discuss the distinction between windowing by event time versus processing time. This difference is vital, especially when it comes to reprocessing historical events. Processing time can often be misleading, which is why tools like Apache Beam offer APIs that allow computations based on event time. This capability is essential for accurately analyzing data as it reflects the true timeline of events, making it easier for organizations to extract meaningful insights. As we explore the broader landscape of data management, it's important to recognize the similarities and differences between databases and operating systems file systems. Both serve the purpose of managing information, but they do so in different ways. Databases organize data in structured formats, like rows and tables or documents, while file systems manage data in files. The practical implications of these structures can vary significantly. For instance, databases typically handle millions of small records with ease, whereas file systems might struggle with such a load. The philosophies behind Unix and relational databases also diverge significantly. Unix provides a low-level hardware abstraction for programmers, while relational databases offer a high-level abstraction that simplifies the complexities of data management. This ongoing tension between the two approaches has persisted since the 1970s, leading to innovations like the NoSQL movement, which aims to apply a Unix-like model to distributed data storage. Throughout our discussion, we've touched on various features of databases, such as secondary indexes, materialized views, and replication logs. These elements are crucial for maintaining derived data systems, which are becoming increasingly common in data architecture. Instead of relying on a single integrated database, organizations are now utilizing multiple specialized systems, each optimized for specific tasks. This unbundling of databases allows for greater flexibility and efficiency. For example, a relational database might support various index types, while derived data systems can be maintained by different software components running on separate machines. This modular approach enables teams to concentrate on their specific areas of expertise, fostering innovation and specialization. Looking ahead, we can expect two primary avenues for composing different storage and processing tools into cohesive systems: federated databases and polystores. A federated database allows applications to access specialized data models while enabling users to combine data from various sources seamlessly. PostgreSQL's foreign data wrapper is a prime example of this pattern. However, challenges remain, particularly in synchronizing writes across disparate systems. While distributed transactions work well within a single system, integrating data across different technologies can be complex. An asynchronous event log with idempotent writes offers a more practical solution, providing loose coupling between components and enhancing overall system robustness. The benefits of log-based integration show up in two key areas. First, at the system level, asynchronous event streams create a buffer that helps the system remain resilient to outages or performance issues. If one component fails, the event log can temporarily hold messages, ensuring that the rest of the system keeps functioning smoothly. This isolation of faults represents a significant improvement over the synchronous interactions typical of distributed transactions. Second, from a human perspective, unbundling data systems allows for independent development and maintenance of different software components. Each team can focus on their specific functionalities, leading to a more efficient development process. Event logs serve as a powerful interface, capturing strong consistency properties while remaining flexible enough to accommodate various data types. Despite the rise of unbundled systems, traditional databases will continue to play a critical role in managing state within stream processors and serving queries for both batch and stream outputs. Specialized query engines will remain essential for specific workloads, ensuring that organizations can optimize their data processing capabilities. However, there's a caveat. As we embrace a diverse array of tools, each with its own learning curves and operational quirks, we must balance complexity with performance. A single integrated product may outperform a system composed of multiple tools, especially for specific workloads. Therefore, the decision to unbundle should be driven by the need for breadth rather than depth in data management. In conclusion, the future of data systems is an exciting blend of innovation and complexity. As we navigate this evolving landscape, the ability to replay historical events, ensure exactly one's semantics, and leverage diverse data architectures will be crucial. While unbundling databases offers flexibility and specialization, we must also recognize the enduring value of traditional systems. By finding the right balance between these approaches, organizations can build robust, scalable, and efficient data ecosystems that meet their unique needs. Thank you for joining us for this episode of Data Insights. We hope you found our exploration of the future of data systems enlightening. Until next time, keep questioning, keep learning, and keep innovating.